Let's look at the Yolo version 3 by Joseph Redmond and Ali Farhadi of the University of Washington. They present some updates to Yolo, where they made a bunch of little design changes to make it better. They also trained this new network that's pretty swell. It's a little bigger than the last time but more accurate. It's still fast enough, don't worry. At 320 by 320, that's the input. Yolo version 3 runs in 222 milliseconds at 28.2 mean average precision. As accurate as SSD but 3 times faster. And as we could see in this figure 1, where we plot the Cocoa average precision with the inference time, Yolo version 3 runs significantly faster than other detection methods with comparable performance. So in a nutshell, the Yolo version 3 is compared to the Yolo has been developed or was developed such that it has an increase in accuracy without much decrease in its speed. Now let's look at the bounding box prediction. Following Yolo 9000, now this is an intermediary Yolo version we have, which lies between Yolo and then Yolo version 3. So following this Yolo 9000, our system predicts boxes using dimension clusters as anchor boxes. Now there's this term anchor boxes which come into play. Suppose we have this image where this bounding box surrounds this airplane. During training, the Yolo model struggles to obtain the x, y values, that's the center, and the width, height values. That when using anchor boxes, instead of trying to get those values directly, what we do is we instead fix an anchor box like this one, where the xy values of the bounding box is given with respect to the anchor box. That is, they actually offsets. The offsets are what we try to calculate with respect to the anchor box, and that's how we regenerate this bounding box. And the same is done with the width and the height. Now we can have many other anchor boxes. So instead of having this anchor box alone, we could also include this other anchor box 1.2 by 0.8. We could include this other one 0.8 by 1.2, and this other one 1.5 by 1.5. But what's important to note here is that these anchor boxes take the form of very common objects we have in our data set, and that's why to select these anchor boxes, generally we use a k-means clustering algorithm, where we get the anchor boxes which look the most like, or which get the most resemblance and shape like the bounding boxes surrounding the objects in the data set. So in this case, for example, that we have this, we see clearly that this anchor box, which is 1.5 by 1.5 with respect to a grid cell, actually looks the most like this bounding box. So instead of getting the bounding box, we'll just get these offsets, the differences between this and this. So the model now spend less time in trying to figure out the bounding box, since all it needs to do now is just to get the offset between the actual bounding box and this fixed anchor box. Now the network predicts 4 coordinates for each bounding box, which are tx, ty, tw, and th. If the cell is offset from the top left corner of the image by cx, cy, and the bounding box prior has width and height pw and ph, then the predictions correspond to this. Now this bounding box prior is the anchor box. So what the authors are giving us here's formula is the offset, or the link between the offset and the actual bounding box values. The offset for the bx, that's for the x value, is this tx as it was set right here, and to get bx we have the sigmoid of tx plus cx, where cx is the offset from the top left corner of the image. Now let's look at this from this diagram right here. We have this tx, ty, and then we have this offset from the top left corner of the image. So we get this cx and cy values, which are given in the grid cell referential system. So in this case, for example, cx equals 1 and cy equals 1. And this means that what our model will be struggling to predict, or what our output will be the tx and ty. And so our model struggles to predict tx and ty, and then after prediction, then we are able to get the bounding box by finding the sigmoid of tx, sigmoid of ty, and then adding up cx and cy respectively to get bx and by. Now, where we're going to use the anchor box values or the prior values is for the bw and bh. For bw, we have pw plus e to the power of tw, and bh times e to the power of th. This pw actually represents the prior or the anchor box's width, and then this represents the prior or the anchor box's height with respect to a given grid cell. And again, here what we'll be struggling to predict will be the tw and the th. So once the model predicts tw, th, we are able to get the pw and ph and bw and bh using pw and ph from the anchor box, and this shows us that a given anchor box will have a different value for bw and then bh if etw and eth remain constant. Looking at the diagram, we'll easily understand this concept. We see this blue right here, which represents the actual bounding box of a given object, and then the ph, which represents that of the anchor box. Now, during training, they use the sum of squared error loss. If the ground truth for some coordinate prediction is t star, so we're supposing a tx star, ty star, our gradient is the ground truth value computed from the ground truth box minus our prediction. So this ground truth value can be easily computed by inverting the equations above. So what's going on here is that what our model actually predicts is a tx and then the ty, as we've said already. But then to get now the bx and by, we just simply have to invert this or make tx and ty subject of the formula. And to obtain this, if we have, say, bx equals sigmoid of tx plus cx, then this, given that sigmoid of x is 1 over 1 plus e to the negative x, we have bx, which is 1 over 1 plus e to the negative tx instead, plus cx. This implies that we have bx times 1 plus e to the minus tx, as we could see, plus, which is equals 1 plus cx times 1 plus e to the negative tx. And then we have bx, that's bx times 1 plus bx times e to the negative tx, which is equals 1 plus cx times e to the negative tx. This implies that we have bx e to the negative tx minus cx e to the negative tx equals 1 plus cx minus bx. We rearrange this and we have e to the negative tx times bx minus cx, which gives us this. Then we have e to the negative tx, which is 1 plus cx minus bx divided by bx minus cx. Now note that the reason we're doing this is because we want to make tx subject of the formula. So with this, now we put log on both sides, and then we have that the log of e to the negative tx is negative tx log e. The log of e is equals 1, so this gives us tx equals the negative of this, because this is negative sign here, negative log of this, which is equals the log of this to the negative 1, which is then equals bx minus cx divided by 1 plus cx minus bx. And then this can be done similarly for ty to obtain this also, by minus cy divided by 1 plus cy minus by. So what this is trying to give us is that once we have a given object, or once we have a given bounding box with the x coordinate of the center as bx, the way we obtain tx for training is that we use that bx minus the number of grid cells before the object divided by 1 plus that same number of grid cells from the x direction before the object minus bx, and then we take the log of that. So once we have this, this is how we obtain tx, and this is exactly what our model is going to be struggling to predict, so that such that once we predict this, we are able to come back to this using this formula. And this actually, as we've said already, helps speed up training. We do the same for TY, and then we move to the BW and TW transformation. For BW, TW, we're using this PW, which stands for the width of the anchor box or the prior. To get ETW, we have ETW equals BW divided by PW. This gives us this. And then finally, we have TW log E, which is 1. Finally, we have TW, which is a log of BW divided by PW. And then we have TH, which is equal to the log of BH divided by PH, which is basically gotten from the same, or gotten by doing the same calculations. So once we have this now, it tells us that once we have a given prediction where we have the width, we simply divide it with the anchor box, find its log, and then this TW now represents the width our model is struggling to predict, or the output level for the width, and then this will represent the output level for the height. So our model doesn't predict the BW again or the BH, but it now predicts TW and TH. Yolo version 3 predicts an objectness score, that's to say whether there's an object or not, for each bounding box using logistic regression. This should be one the bounding box prior overlaps a ground truth object by more than any other bounding box prior. If the bounding box prior is not the best but overlap a ground truth object by more than some threshold, we ignore the prediction. We use the threshold of 0.5. Now this system only assigns one bounding box prior, that's one anchor box, for each ground truth object. If a bounding box prior is not assigned to a ground truth object, it incurs no loss for coordinate or class predictions, only objectness. We shall look at our generate output method, which we shall rebuild since the Yolo version 3 comes in with some concepts like the anchor box. Now here we define this 3 anchor boxes. This one with its height and its width, this the height and the width, this the height and the width. So this is the first, the second, and then the third. Now when we define this anchor boxes like this, it simply means for a given cell, for this anchor box right here, the height of the anchor box is 1.3 times that cell, and its weight is 1.3 times that cell. And then for this anchor box, the height is 2.3 times the cell, and the weight 1.3 times, and this 1.3 times, and the weight 2.3 times. The way we also define our output level also changes as we include this anchor box dimension. In this example, since we're working with 3 anchor boxes, here we'll have a 7, that's for the output level. It will be a 7 by 7, that's for the split size, if the split size is actually 7, because the split size, as we'll see, could also take different values, but now we're supposing it to be equal 7. Then after this, we have the anchor box length, in this case is 3, since we have 3 anchor boxes. Then the number of classes plus 5, so there we go, we have 27 right here. So instead of previously this 7 by 7 by 27, this is what we had previously. Now we have 7 by 7 by 3 by 27, because each anchor box produces its own class, bounding box, and objectness predictions. Again, here as previously, we have to go through each and every bounding box, but for each and every bounding box, we are going to do modifications on our output level based on these anchor boxes. So again, here we go for each and every bounding box, and then for each and every anchor box, which is simply this. Now here is going to look similar to what we had in the Yolo version 1, but for 2 major differences. The first difference is that instead of working with the BX, BY, BW, and BH, we now want our model outputs to be TX, TY, TW, and TH. So this simply means that just like we did previously, we shall get these values, and then we shall use the transformation we saw on the slides to obtain TX, TY, TW, and TH. Then the other consideration is that from what we had in the paper, we only assign one anchor box for each ground truth object. And here again they say if a bounding box prior that if the anchor box is not assigned to a ground truth object, it incurs no loss for coordinate or class predictions. So this simply means that for all these 3 anchor boxes we have here, we shall pick out just one. Suppose we just pick out this one. It means that the output labels will be defined such that at a given cell position, it's only this anchor box which will have the bounding box and class cause, while for this other 2 anchor boxes right here, it will be as if there were no objects in that cell. So this will be the only anchor box used to represent the object in that cell. We have just picked this particular anchor box at random, but the way it's done is such that if we have this kind of object right here, that's this airplane, and that we have this anchor box, this other one, and this one, clearly we see that this anchor box here, that's this anchor box with height 0.8 and width 1.2, has the greatest IOU with this true bounding box right here, this bounding box. We see that this anchor box has the highest IOU, followed by this one, and then finally this. So this simply means that this anchor box wouldn't be used in finding the bounding boxes for this object or for this aeroplane we have right here, while it's only this which is going to be used, since it has the greatest IOU compared to the other anchor boxes we have in here. Let's get back to the obtention of those B values. To obtain those B values, when given, for example, this image, suppose that the image has a height of say 100 pixels, so we have 100 pixels, and then the width 100, so we have 100 by 100 image, and that we have a split size of 7. So as you could see here, we have 7 boxes. That's we have 1 2 3 4 5 6 7, the width dimension, and here 1 2 3 4 5 6 7. So our split size is actually equals 7. Supposing we have this object right here was positioned in this width dimension right here. Let's do this. Could link it up like this. So this position is given that this is from 0 to 100. This position here is 64. So this distance like this, we have 64, and then this other distance in the height dimension, we could do this up here actually. So we have this distance 64, and then the height dimension, this distance up to this is 21. But converting this into the split size reference, that's 7 by 7, that we're leaving from 100 by 100 to 7 by 7 reference, this will be 21, for example, for the height, divided by 100 times 7, and that will give us approximately 1.5, which is logical, since as you could see here we have 1, this is like 0.5. Consider that this is 0.5 of the cell, so we have 1, 1.5. This is 1 2 3 4 5 6 7, and if you calculate 21 divided by 100 times 7, you still get approximately 1.5. Now for the width dimension, it's 64 divided by 100 times 7 is approximately 4.5, and if you go, we have 1 2 3 4, and if we take this to be the center, then this is 4.5. So that said, when we're given this center position or any other position, we are able to convert it into our split size using the fact that we could have the value, that is, let's say whatever value, divided by 100, or divided by the image dimension times the split size. So in this case it's 7. So that's what we use to transform it into this our new image space. With the Yolo version 1, we had seen something like this already. We had done this. So here for every value, that's x min, y min, x max, y max, we simply took the value and then divided by the width for the x, and then for the y's we divided by the height. For now, we haven't yet multiplied by the split size as given in the formula, because in the formula we have the value divided by the width times the split size. Now we're taking those values and then passing this generate output function right here via this bounding boxes. We've seen this already. So we have this, we have the anchor box, we have the output label, which we've seen. Now we're taking the values for the x mean, y mean, x max, y max, which are those values. Then, since what interests us isn't the x mean, y mean, and then the x max, y max values, which are these points and these points, we have to work with what we are going to be using, and that is the centers. We're going to use the center and the width and the height. So that said, we shall convert this x mean, y mean, x max, y max into the center and the width height. To do that, we shall use the simple fact that if we have the x mean, y mean, x max, y max, we could obtain this center by finding the midpoint of this 2 points. So if we have the x mean here, and then here's the x max, because we're going from x mean to x max. So the midpoint of x mean, x max will fall on this at this point. So we'll have the bx, that's the center, or the x coordinate of the center. And then for the y mean, which is this, if we're going from this y mean, and then here we have y max, the midpoint will fall here, and that will be our by, the y coordinate of the center. So now once we understand it like that, we could have the center from the x mean, y mean, and the x max, y max. And then once we have the center, we could also get the width and the height by simply subtracting the x max with the x mean. So we have x max minus x mean gives us the width, and then x or y max minus y mean gives us the height. And it's this formula we apply right here. After getting this from the bounding boxes, we get the x center and then the y center by finding the midpoint of x mean, x max, y mean, y max. Then the width and the height, we simply do subtraction, and that's fine. Now let's keep this aside for now. Let's take this off from here. Let's put it right here. Okay. So there we go. Now we have this, and then once we have that, now recall that as we had seen here, we had just divided by the width and the height, and we were yet to multiply by the split size. And so from this, we see that to obtain the bx center and the by center, we have to simply multiply by the split size, and that's basically an application of the formula we had seen previously. Now we have the bx and the by, as we could see, and then for the widths, we also have to multiply this by the split size. So we take this, multiply by the split size. So now that's fine. We have our b's. If also you take a close look at this relationships linking the b's and the t's, you'll notice that there are these offsets cx, cy, and we also have this pw, ph, which represent the width and the height of the anchor box. Now we've defined this width and this height right here. We've defined this pw and ph for our 3 different anchor boxes. The first we had 1.3, 1.3, the next 2.3, 1.3, the other 1.3, 2.3. So these 2 values have been defined. It means if we're given bw, bh, we could obtain tw and th. Now what about this cx, cy, which happens to be the offsets? Let's better understand this by looking back at this our diagram. Now we have this 100 by 100. We've now seen how to look at it as a 7 by 7 image. Now to obtain these offsets, we'll simply count the number of boxes we have just before the cell where the object is found. So to obtain the cx, we have here 1, 2, 3, 4, and then to obtain the cy, we just have 1. So here our cx is equals 4. So cx equals 4 in this case. This equals 4. and then the cy is equals 1. But for this particular example here, this other example, we have cx and cy both equals 1 because the object is found here. And to get to this object, if we move in this x direction, we just have one box before getting to the object, the box which contains the object. So here we have cx equals 1, and then for the y, if we're going downwards, we see we just have one box before getting to this box which contains the object. So cy equals 1, and that's how we obtain this. Now if we get back to the code, this simply means to obtain this offsets, we could take in this bx center, so we could have bx center, by center, and then find or round down this value to the nearest integer, and that simply means finding the or passing this as an int, because here we have floats, and then passing this as an int will take us to the lowest integer from below. So if we have a 4.5, after passing in this, we'll now get a 4. And this is very logical, since if going from this to this gives us 4.5, that's now a 7 by 7 reference, then the lowest possible whole number, which is closest to this 4.5, or rather the highest possible whole number closer to the 4.5 from below, is 4, since the object is at position 4.5. And then for this, if we have, say, if let's maintain this, if we go on the y direction, we have 1.5. So because this was 4.5, 1.5, we understand that if we have to round down this 4.5, we will have 4, and then if we have to round down this, we would have 1, and it comes back to the answers we had previously. And this justifies why we have this here as the offsets. So we have the center cell. So here we go, we have the offsets. Now we have the offsets, that's the cx, cy. We are ready to obtain the t's from the b's. Now looking at this, we define this function bounding box to output. So now we have our bounding box, or the bounding boxes, which are the b's. Now the output here are the t's. Actually, we're trying to convert the b's to the t's. That's what this function does. So we have the b's to the t's. Let's take that back. Notice how we are gonna implement this formulas right here, where this bx, by's are the object centers, the cx, cy the offsets, pw, ph the anchor box height and width, and then the bw, bh the object width and height. That's what we have here. We have the b minus the offset divided by 1 plus offset minus b. Again here, same for the this for the x, this for the y, for the height, and then this is for the width. After defining the tx, which is this tx, ty, th, tw, we can now go ahead to the next step, that is computing the IOU between the bounding box and the different anchor boxes. We had defined this IOU function previously. Here it is. Here's the exact position where we actually apply this IOU method. We see here we have this first part, that's this first box, which is the bounding box, and then this next part is the anchor box. If we start with the bounding box, you'll notice that we have x min times width, y min times height, x max times width, and then y max times the height. And this is simply because these values here were gotten after dividing each of them by the width and the height respectively. So this means to obtain the actual x min, y min, x max, y max values, we need to simply multiply them by the width and the height, since previously here we had divided them as we see here. So now that we've gotten the bounding box for the object, which is this, we can now go ahead to look for the anchor box values. Now to look for the anchor box values, supposing we have this image with split size 5, So even if we have an image of dimension 1000 by 700, in this split size reference is now a 5 by 5 image. So each of these boxes now represent a single unit in this image, unlike previously where a single pixel represents a single unit. So in this case, if we have an object at this position, let's pick an object here. Let's say we have this object right here. For the bounding box, we would clearly have something like this right here. We would have this bounding box. And then for the anchor boxes, the width, if you take this anchor box for example, both the width and the height will be 1.3 times the size of each cell in this split size reference. So this means that if we have the center right here, then an anchor box will be like going 1.3 times the original cell, or 1.3 times any given cell we have in here. Now if we have 1.3 times, if we have to move from the center outwards, then we have to go halfway and then downwards halfway to complete. So this is gonna be like 0.65, since 0.65 times 0.65 is equal plus 0.65 is equals 1.3. So in this case we have to go, this is 0.5. obviously we suppose that this is the center of this, it's not well drawn, so this is 0.5, this is 0.5. we add an additional small 0.15 right here, and then similarly here, and then we repeat the same here. We have something like this, we have something like this, and there we go, we have our anchor box. So that's our anchor box, which we draw out right here. There we go. If we pick out this other example where here we have the height 2.3 and the width 1.3, here instead we are going to have to go 2.3 divided by 2, that is 1.15 times upwards, and then 1.15 times downwards. So here we have this 0.5 going here is 1 to the next center. From the center to the center is 1, so we have 1.15, which should be around this, and then we repeat the same here, the center 1, and then around this. This is maintained since we're still 1.3, so we would have an anchor box this time around, which should be like this. So our anchor box will look like this now. We see that clearly this first anchor box looks closer to the original or the object bounding box, and if we were to compute the IOU score, this anchor box will have a higher score as compared to this other anchor box here. But now the only problem we have is that the bounding box coordinates, that's the x min, y min, x max, y max, have been given to us in the pixel reference. That is, if the image is say 500 by 500, then it has been given in that reference, as compared to these calculations we're doing here in the split size reference. So what we first do, as we've just seen now, is to get the cell position, or rather to get this object position, the object center position. As we've seen, we've gotten this already with the b's, that's it right here, that's the bx, and then we subtract the anchor box width divided by 2, like in this case is 0.65, so 1.3 divided by 2 is 0.65. That's how we obtain, for example, where this is, supposing we went here, we have 1, 2 and a half, 2.5, so we'll go 2.5 minus 0.65, and then we'll follow this position right here. So that's why we do this right here, to follow this position. And we repeat the same for all this. We have by, we have the center, the y coordinate, minus 1.3 divided by 2, we obtain this other position. And then for the max, we instead do the center plus the anchor box divided by 2, or plus the values that we have here, that's the width and the height of the anchor box divided by 2. So if we have this position, we have plus 0.65, and then here we have plus 0.65, and that's how we locate this anchor box x max, y max coordinates, and then the x min, y min coordinates in the split size reference. But now we've gotten this in the split size reference. All we need to do now is to convert it back into the pixel reference. That's the image, the original image reference. And to do that, we need to simply reverse the process which we did to leave from the image to the split size reference. Recall that what we did previously was, if we have a certain point, let's say a point P, all we needed to do was to divide by, let's say, width or the height, and then multiply by the split size, which in that case was 7. So if we have a width of, say, 100, we did this, we divided by 100 and multiplied by 7 to get to the split size dimension or reference. If in this case the split size is 5, instead of 7 we'll have 5. So that's what we did. Now to reverse this process, what we do is we instead divide by the split size and then we multiply by the width or the height. And that's what we do here. We divide by the split size, multiply by the width if it's in the width dimension, and here divide by the split size, multiply by the height. For this, the same, divided by the split size, multiply by the width, divide by the split size, and multiply by the height. Once this is done, we've now gotten the exact positions of the anchor box, and we are set to compute the IOU score for each anchor box and the bounding box. We also ensure that every time we have a value which is less than 0, we just fix it to a 0. Now, as you could see here, we have this list box IOU, which is going to contain the IOU score for each of these anchor boxes. And that's why here we're supposed to define this. We called it box IOU. So we have box IOU, which is this empty list. So before getting to this, we define the empty list. For each bounding box, we define an empty list where we store the different IOU values or scores for between the anchor boxes and that bounding box. Here again we have the bounding box, and then here we have the anchor box, which we've just seen exactly how it was computed with this. We will not be needing this. We'll take this off. Then we have this last part right here. Shift this, where for this box IOU we have here, we're going to look for the box with the highest IOU score, and that's why we do this arc max right here. Once we get the box with the highest IOU score, notice how we leave this, we get out of this loop. Once we get out of this loop and we get the box with the highest IOU score, we now use it as we had seen with the Yolo version 1 to first of all select the anchor box and then pass in the bounding box values. Also notice how we're doing this with this bounding box to output method, which we've defined, which leave from the B's to the T's. So let's take this off. There we go. And now what we pass here as anchor box is the particular anchor box which has the highest IOU score. So that's why here we specify highest A. So we'll specify the highest anchor box, which is passed. The offsets we've gotten already. The B values we've gotten already. And then we now put a 1. That is, we'll put this value of 1 after selecting the particular class position as we've seen previously in the Yolo version 1. In order to test this method, we shall include the highest A. So we shall print out the highest A right here. Run this, run that. There we go. Now we've picked an image of just one bounding box so that we just get to see clearly the exact anchor box for just that one object bounding box. And here's the image in question. The object in this case is a person, and here we have the true bounding box surrounding the person with now our grid cells of dimension 7 by 7. We have 7 cells, since we've picked a split size of 7. Now for the first anchor box, that is 1.3 by 1.3, let's pick a different color. Let's take this. Let's get back. Okay, so now let's come to this again and pick a different color here, green. We shall have from the center of the object about 1.3 times, that's 1.3 times each of these grid cells. So we just kind of draw a box around this. So this anchor box will be like this. It's not exactly the same, but it should be around this. Okay, so that's our anchor box for 1.3 by 1.3. Now let's pick another color and draw for a width of 2.3 and a height of 1.3. In that case, we have this same height, but the width is extended, so we would have about twice this, and we add 0.3 of a grid cell to make 2.3. So we should go, if this is 1.3, then 2.3 should be about 2 times this, but with the same height actually. So we would have something looking like this. It's not exactly the same, but it should look around about this size. See, this is the same height, 1.3, like the previous anchor box, but now we have this width which is increased. Let's reduce this a little. It should be like this. Okay, so there we go. That's our anchor box where the height is 1.3 and the width is 2.3. Now let's pick another one. This time around, let's get back. Let's pick another one. This time around, let's pick this color, orange, and then from the center we have 2.3, 1.3. Now we'll have something like this. Oh, we've picked the circle. Let's take this back to this, and now let's have this right here. We'll have something like this. That should be 2. Yeah, it should be around this. So we see clearly that for all these 3 anchor boxes, this one looks most like the actual bounding box, and that's why right here this 2 was selected, because here we have the width of 1.3 and a height of 2.3. We also see that in this output generated, the 3 anchor boxes we have are this are the 3 anchor box outputs we have at this position right here. We have this, and this, and that's only this last one, which will be used when computing the loss function based on the class predictions and the bounding box coordinates. Also recall from the paper that even though this selected anchor box will be used for the objectness loss, class loss, and bounding box loss, this other 2 here will be used for the objectness loss. And so this means this last position has to be changed to a 1 to indicate that there is an object in this particular anchor boxes. And so what we'll do here is we'll say for A in the length of anchor box, or in the range, for A in that range of length of anchor boxes, we shall take this, we shall repeat this. So we'll have something like this, put that out, and then at the last position, that's 26, you see here we now have A. So we'll make sure that at the last position we have a 1 for the objectness loss calculation. So we'll run that, run again, and there we go. We now have 1s, indicating that they are objects, or that there is an object in this 2 anchor boxes, but with the difference that we don't have to do calculations of the class loss and the bounding box loss using this 2 anchor boxes. In this next section on class prediction, we'll see that each box predicts the classes the bounding box may contain using multi-level classification. So we didn't use softmax as we have found it unnecessary for good performance. Instead, the other uses simple independent logistic classifiers. During training, they use binary cross entropy loss for the class predictions. This formulation helps when we move to more complex domains like the open image dataset. In this dataset, there are many overlapping labels, that is, woman and person. This simply means that we may have the same object, which could be 2 different classes. So we could have an object representing a woman and that same object representing a person. Whereas if we're using softmax, then we're supposing that that object can only belong to one class, which may not be the case for some data sets. Then the next we go to prediction across scale. Yolo version 3 predicts boxes at 3 different scales. The system extracts features from those scales using a similar concept to the feature pyramid networks. Then to the base feature extractor, we're going to add several convolutional layers. The last of this predicts a three-dimensional tensor encoding bounding box, objectness, and class predictions. And the experiments with the COCO, they predict three boxes at each scale. So the tensor is n by n, that's split size by split size, by 3 by, now here we actually have the bounding box predictions plus the objectness predictions plus number of classes. So here we would have 27 in our case. So this n by 3 by 27 for the 4 bounding box offsets, 1 objectness prediction, and 80 class predictions as offset. Then we take the feature map from 2 layers previous and upsample it by 2 times. We also take a feature map from earlier in the network and measure it with the upsampled features using concatenation. This method allows us to get more meaningful semantic information from the upsampled features and finer grained information from the earlier feature map. We then add a few more convolutional layers to process this combined feature map and eventually predict a similar tensor, although now twice the size. We perform the same design one more time to predict the boxes for the final scale. Thus, our predictions for the third scale benefits from all the prior computation as well as fine-grained features from early on in the network. Also, k-means clustering is used in determining the bounding box priors. These bounding box priors are the anchor boxes which we've seen already. Let's better understand prediction at scale using the mobile net feature extractor or backbone. After passing an image into the mobile network, we have this output tensor of dimension of shape 7 by 7 by C1, where C1 is a channel number. This tensor right here is passed into a head, and then the output of this gives us this tensor of shape 7 by 7 by A, where A equals 3 in this example, since the number of anchor boxes or prior boxes we're working with is equals 3. So we have 7 by 7 by 3 by 27. And it should be noted that this output here is for one scale, that is the scale with split size equals 7. Now what we do next is we upsample, or before the upsampling, what we do is we get this output from previous layers. That is, we have this final output, but before generating this final output, we have some intermediary layers from a given previous layer up to this final layer right here, which generates this output. So we get this output from a previous output layer, which has an output, or which gives us this output tensor, whose height and weight is twice the shape of this output. So here we have 14 by 14, which is twice, where 14 is 2 times 7. And so to make use of what we've learned from the layers after this output layer here, or this intermediary output layer up to this final output layer, we are going to upsample this output tensor right here. Simply upsampling means we leave from this 7 by 7 to a 14 by 14 output tensor. Then, since the height and the width are all the same, we do concatenation on this channel dimension. Now this concatenation is done such that we have now C2 plus C3 equals C4, and we have this output tensor 14 by 14 by C4. And then we pass this through another head similar to this, and what we get is 14 by 14 by 3 by 27. This step is repeated again, where we look for another intermediate output, which in this case is 4 times the final output and 2 times this other intermediate output. So now we have 4 times 7, which is 28. So we have 28 by 28 by channel size C5. And then we upsample this to get 28 by 28 by C6. We do the concatenation. We get this output. We pass through the head, we have this output, which is 28 by 28 by 3 by 27. And so yeah, we have this model which generates predictions at 3 different scales: this scale, this, and this other scale, where this scale is twice the final output scale, and this other scale is 4 times this final output scale. For our practical session, we are not going to use 3 scales. We'll just work with just 2 scales, that is this and this scale, one which is 7 by 7 and the other one 28 by 28. So yeah, we'll upsample this output from here twice, such that we leave from 7 by 7 to 28 by 28. This now takes us to the data generator. For our data generator, as usual, we have this input image, and then now we're working with 2 scales. We shall have this 2 outputs. If we had 3 scales, we would have a Y3. If we consider the split size to be 7, yeah, we will have batch size. So this will be batch size by 7 by 7. From this split size by anchor, that's 3 number of anchor boxes by 27. And here we would have batch size by, you see here we have split size times 4, so we have 28 by 28 by 28 by 20 by 3 by 27. Also note that the bigger the split size, the better we could, or the better the model will be able to predict or detect smaller objects. And so depending on your data size, or your data set rather, you could choose this split size values. So coming back to this, we have 28 by 28 by 3. So that's what we get now. We have this 2, which will then later on just pass into our model as this output list. Just like with the Yolo version 1, we have this image, we have this empty numpy array. We pass the image array into our numpy array, then we get the bounding boxes, we get the output labels. Here we have y1 and then we have y2, which we now pass as y1 y2 right here. And then once we get this, we pass it as a list, as we've seen already. So let's run this, run that, and there we go. We are going to be using the MobileNet version 2 backbone, and then extracting the final output and an intermediate output. Let's run this, get the summary right here. You see this output comes up with a split size by channel dimension. Then we could scroll up to get to the intermediary output, where we're gonna have the split size times 4 by split size times 4, in this case 28 by 28. So this means simply that if we get to this, we could extract this output actually. So here's our intermediate output, and here's that layer which produces that output. And so we'll copy this name and use it to generate a model output, where we will have the 2 outputs concatenated. So right here we'll have this, print this out, take this off. We're normally returning this base model. Now notice that we're gonna have this block 6 expand relu, that's gotten from this right here, and then we have the out relu, that's gotten from this, and then we pass it into these 2 variables, block 6 output, out relu. We have the outputs, block 6 output, and then out relu, similar to what we had here. So here is like our intermediate output, or rather here is the final output, and then the y2 is the intermediate output, since here we have this split size times 4, 28 by 28. So since we have this as our intermediate output, the second one will ensure that here we would have out relu, and then we have that. We have now the intermediate output, block 6 output. Take this off, and then we could rerun our model. This is fine. Let's look at the head. Now with the head, we shall stack some conv layers in here. but making sure that the output tensor, after passing this tensor into this head model or head layer, would be such that after reshaping we could get this kind of output where we would have the split size by number of anchor boxes, which in this case 3 by 27. And as you could see right here, we have this conv layer, this other conv layer, this conv layer. We ensure that this output dim right here is defined such that it could fit the output tensor shape considerations. This is actually what this output dim looks like. You see here we have 3 by split size times 27. So that's it. Then we have the layer normalization, global average pooling, and then the reshape. With the reshape, we're gonna have the exact tensor shape we need for the output. Now we simply call this, and then that's our head. Once this is done, we have this definitions. Here we define the inputs. So we have this input image, which is now passed into our base model, which we defined already. This base model has two outputs, the out relu and the block 6, which we've just seen. So right here we will have this out relu block 6. There is it. Normally this should be out relu, and then take this off. That's it. So we have out relu block 6, and that's it. This out relu is now passed into this head, just as we saw in the slides. Then we have this output here, which we call head 7. Also notice that we have this output shape, which is actually designed such that we could reshape an output tensor from this output dimension or this output dim we have here. So when we pass this output shape in here, you see how it's passing this reshape, and then we could reshape our tensor exactly as we want it to be. So that's it. Run this already. Now here we have this head 7, which now we shall upscale, and we shall use a conv to the transpose to upscale. We upscale this just once by using a stride of 4. If we had a stride of 2, we'll get from an input of 7 by 7 to an output of 14 by 14. So here we have the stride picked out to be equal to 4, such that after upscaling we get to the 28 by 28 output. Then this is before concatenation, so we call this pre-concat. Then we now get into concatenation, where we get this upscaled output here concatenated with the block 6 output, which is an intermediate output. And this is exactly what goes on in here. So we get in this up sampled or upscaled output, and then we get in this intermediate output, and then we concatenate them, then we pass through the head again. So just like we did here with this head, we again pass this through this head, and we have the head 28 now. Then our model returns the two heads, that's the head 7 and the head 28. This has been run already. Let's just rerun that. So here we have this model output right here. We have the two heads, the 7 by 7 by 3 by 27, and then the 28 by 28 by 3 by 27 for the two scales, while we just have one input. We now get into the training and optimization. The loss function we'll be having will be similar to what we had already, but with some slight differences. Recall that while creating our data set, that was at the step, for the 3 bounding boxes we have, one will be used in the class loss, object loss, and the bounding box loss, while this other 2 will be used only for the objectness loss. This means that apart from having a 1 at this last position right here to show that there's an object, we also have to change this 0 value to 1 and this other last 0 value to a 1, such that this 2 anchor boxes right here will be considered to be having objects, or be considered to contain objects. That said, we shall add this other extra part. Let's comment this for now. For now, we just have, we see for A in the range of the anchor box length, we ensure that this last value right here is equals 1. Now let's run this again. You now see that here we have a 1, here we have a 1, and obviously as before, here we also have a 1. And so when computing the loss, we shall take into consideration this 2 only for the objectness loss, and this 1 will be for the rest of all the different loss parts we have which make up the Yolo loss. But the way we define this loss function right here was that we consider, for example, the way we created this target and the way we used it for this object loss right here was that we consider that there is an object in a given cell if this target value, that's this last value, is equals 1. So this means that for now all is well. But the problem here is that if we have, or if we make the same assumption for this others, that's for the object class loss and then the bounding box loss, the class loss and the bounding box loss will be computed for this 2 anchor boxes, since this value is equals 1, as they are only computed where this value is equals 1, as you could see right here. So where this value is equals 1, that's when we compute the class loss as we had in the Yolo version 1. But now we have some cases where this may be 1 and we don't want to calculate this class loss, and that's the case of the anchor boxes whose IOU scores are in the highest in the given cell. And so to solve this problem, what we could do is to modify this criteria right here for which a given anchor box will be used in computing the class loss or the bounding box loss. To solve this problem, what we're gonna do is, instead of using this last item here or this last value to see whether a given anchor box will be used for the class loss or the bounding box loss, we are gonna use this second to the last value, given that whenever we have to do class, or whenever we have to use a given anchor box for class loss or bounding box loss, this value is going to be different from 0 rather. So since this second to the last value we have here 0, here we have 0 for when we are not supposed to use it for both the class loss and the bounding box loss. And that said, what we could do now is we just simply modify the loss right here. So we have where, that's for the object class loss. Here we have where this value, but instead 25, that's the value before, where that value is different from 0. So when we have the value to be different from 0, then we can apply the class loss and the bounding box loss. So here we have 25 different from 0. Then here we have 25 again different from 0. And that's it. We've completely modified this. We run the cell, compile the model, and then start the training. After overfitting on one image, here's what we get. Let's interrupt the training. Let's now test our Yolo version 3 model. We define the input test image. We have the anchor box list, which is made of these 3 different anchor boxes which we had seen previously. We convert the image to array, and then we have this get boxes method right here. Below we'll see how this get boxes method is called. We have the 2 scales. Notice how we define the split size equals 7. So here we have 7 and then 28. So we shall do or call the get box method in such a way that we extract the boxes for one split size, and then for the other split size we also extract the boxes. Fortunately, we have the non-max separation method, which will at the end permit us to take away some boxes which surround the same object, since now we have this 2 scales. That's normal that one scale will have a box and the other will have a box. Supposing we just have one box for an object, then this will produce a box, this will produce a box. And also, given the fact that we'll have several anchor boxes, it's normal that we will have many boxes surrounding objects before the non-max operation. Now let's get into the getBox method, which generates the final boxes and the final scores. In this getBox method, we pass in the output, that is the output from the model, and then we also pass in the scales. So right here we have for each scale, and then inside this we have for every anchor box. We define the split size here to be the current scale. So like when the split size equals 7, we would have a split size of 7. When it's 14, we'll have a split size of 14. Then the output will be for a given scale and a given anchor box. So see here, here's a scale, and then here's the anchor box. We'll define the threshold to be 10, and then the bounding boxes is those outputs for which this value here is greater than the threshold value. We get the selected outputs, and we also get the objects. That is in fact the classes from this selected outputs. Now we get into the bounding boxes which we had gotten here, based on the fact that this value is greater than the threshold value. For every box in the bounding boxes, we want to obtain this bounding box coordinates, that's x min, y min, x max, y max. Now to do that, as you can see here, we extract these values from 22 to 27, which we've seen already. This is actually from 22, this is actually 22, 23, 24, 25, and then 26. And then once we extract this value, the way we get the center values is by simply applying what we had in the paper already. Recall that when creating the data set, we had the B's and then we generated the T's. Now, when doing prediction, we are not interested in working with the T's again. So we use the T's which were predicted, and then from the T's we extract or we get the B's. And once we get the B's, we now have this x center, y center, x width, y height. Now, notice the way we use this formula right here. We have the sigmoid, which comes clearly from this, the sigmoid of tx plus cx. And then this sigmoid of ty plus cy. Here we have the anchor box width times e to the power of tw, the anchor box height times e to the power of th. And that's what we're applying here. Here we have the sigmoid of tx, here's our tx, which has been predicted, plus cx. Then sigmoid of ty plus cy. Here we have the width of the anchor box, which is actually this, times e to the power of tw, the height of the anchor box times e to the power of th. And so it's very important that this anchor box defined here is exactly the same as what we used initially, so that we have matching values right here. Then once we get this, we convert this to minimums by simply subtracting the width divided by 2 from the x center. We repeat the same here, and we do same for the x max and the y max by doing the addition. Then we restrain the values we get for the x min and y min, same for the x max, y max. Then we get the final boxes together with the classes. Also, as you may have noticed, we have this image width divided by space size, which was added right here. The reason why we have this is simple. Now, what we get here is in the split size referential. And so to bring this back into the original image referential, we need to simply multiply this by the image width and then divide by the split size. So that's why we have this, and then this, and then this, and then this right here. Now, once we get this final boxes, let's run this part, we'll run this. Once we get this final boxes, as you could see right here, we now just repeat the same process we had already from the Yolo version 1. So we apply non-max oppression, and then we use OpenCV for us to visualize the predictions and the different bounding boxes. So run this, and there we go. We have these 2 persons detected correctly.